we are going to talk about learning to rank, and then the work that we've done also to integrate this whole process directly into Solr. My name is Michael Nilsson. I am a software engineer here at Bloomberg, and this is Diego Ceccarelli, also software engineer here at Bloomberg. And together we've developed this plugin along with Joshua Pantony, who's sitting right over there. So if at the end you guys have any questions about this for us, feel free to come up to any one of us, or also stop by the Bloomberg booth. We'll be there too, answering questions. So just to give you guys a brief introduction, we're going to cover a little bit about search at Bloomberg, which Diego will talk about, and then from there we'll dive into why you would even want machine learning for search, followed by kind of what learning to rank is, or machine learned ranking, and then from there I'll take it and dive into learning to rank and the actual integration that we've done as a Solr plugin. So with that, Diego, take it away.
So, can you hear me? Okay. So thanks, Michael. I'm Diego Ceccarelli. I started to work with Solr in 2010 while I was working as a researcher at the National Council of Research in Italy. Before talking about learning to rank, let me spend 2 words about my company, Bloomberg. So Bloomberg is the largest provider of financial data in the world. As you know, our main product is the terminal that you can think as a browser where each page corresponds to a function that allows our user to interact with a particular type of data. We have many types of data, and as you can imagine, for us, it's really important to provide search on this data. So we really care about search, and for us, it's really important to be able to provide results, really accurate results in a real-time fashion. I work in the new search team in London. So among all the different type of data that we provide, we have also a large aggregator of financial news. And my team in London is led by Ramkumar Iyengar and provide the search over this news. So I put some numbers in this slide just to let you understand the size of our problem. Of course, we provide search through Solr. Every day we have 8 million searches, and we update the index with 1 million news stories every day. And currently our index contains 400 million stories. I stole this number from Ramkumar's presentation. So if you want to know more about news search and what are the challenges, please go tomorrow to his presentation. It's in the last session of the conference. So as I said, our search service is supported by Solr. Of course, we don't have only news search. We have also other type of data that must be searchable, and we use Solr in many different contexts. This was not the first choice. Over the year, we tried different solutions. We developed our proprietary solutions, but in the end, we decided to use Solr because the company really believes in open source. Why Solr? Because it's a large community. It's an Apache project, and we really like that there's a large feature set that is continuously growing. And of course, if you want to add a feature, it's not so hard to add. So as we show, we add a new feature to the Solr. Of course, we are not only using the service, but we are also contributing by fixing bugs and contributing with new features in the code. Okay, so let's start with learning to rank. But before explaining what is learning to rank and how we plug it into Solr, let me explain you why we decided to do that. So let's make an example. We have our search service, and we want to test our ranking function. So what you usually do, you search for something, so Solr, and you get some results. So we started our service now, so we don't have a big index. And for this query, we get only 2 results. The first one is not relevant, so I put it in a red box. The second one is really relevant for the query, and I put it on a green box. So, okay, are we happy of our ranking function? No, because the first result is not relevant. So we call our search expert, and we ask him to try to fix the ranking function. And this is something that is not hard in Solr. For example, if you use this map query parser plugin, you can change the weights of some fields and get a different ranking function. So in this case, our search expert decided to boost more the score on the title of the query, and the ranking changed. So now we are happy because our relevant result is in the first position. But now our crawler produced new documents, so we add new documents to our index, and running again this ranking function, we get a not relevant result on the top. So again, our search expert has to fix the ranking function, and it does that by changing the weights on the previous field, but also adding a new field that is clicks, is the number of clicks that we saw in the past. So we try to add a feature that represents the popularity of our documents. So with this, adding this new field and changing the weight, we get a different ranking, and now we are quite happy because we have a relevant result on the top, but we have still a relevant result on the bottom. So again, our search expert add a new field that is the time elapsed from the last update. So we boost more the freshness of the documents, and magic now we have a perfect ranking. We have 2 relevant results at the top, and we push down the not relevant results. Okay, fine, we found a perfect ranking function, but then we start looking at other queries. So Solr is okay, but then we look for Lucene, and we get 5 not relevant results on the top, and then we can search for other things like Austin or Bloomberg, and so on, and it doesn't work. So we need to find a new ranking function. So the takeaway message of this is that it's really hard to manually tweak the ranking function manually, so you really need to find an expert in the domain or a magician. So this is another example. We have a service at Bloomberg, and our ranking function in this service uses 2,000 different parameters, and we tune the ranking function on 8,000 different queries. So in the past, doing this by hand was quite hard and time-consuming. So that's why we decided to use machine learning for doing this. So machine learning allows to avoid to do this manually. And I will show you better now how it works. So in this slide, we have the search pipeline, the standard search pipeline. So what happens? We have a user typing a query and against an index that contains, in this case, different types of data. So our index contains documents that could be about people, about news, about commodities, and so on. And from the index, we retrieve the top K results that usually are 10, okay? So this is the standard search pipeline. In a learning to rank setting, we have this, but instead of retrieving the top 10 results, we retrieve a larger number of results. So usually it could be 1,000, 2,000. And then these results are sent to a ranking model. So let's say that we retrieve the top 1,000 results. These are sent to the ranking model that use a learned model to re-rank the top 1,000 results, and then we return the top 10 results from the ranking. Okay? Why we do that? Because the ranking model has a more complex model that is more complex, so it takes more time to do that. And so the idea is that you want to compute, to use the model only on the top results and only on that. So the assumption here is that in the top 1,000 document that you retrieve from Solr using the standard function, you have the relevant results. And then you want just to push the relevant result on the top using the re-ranking model. So, okay, we have a re-ranking model, but how do we create a learning to rank model? So in order to learn a new ranking function, you need a training pipeline. So this is a process that happens offline. You can have this once per day, once per week. And it's quite similar to the online setting. So I'm going to describe more in detail this now. So let's start with the beginning. So what you need for learning a new model, you need a training set. What is a training set? Is a set of queries that you decide, and then for each query, you know which are the relevant documents and then not relevant documents. There are two different ways to create a training set. You can use explicit data, so you really ask to a set of judges that are expert in the domain to tell you which are the relevant documents and the not relevant documents, or you can use a crowdsourcing system from the web. And then we have the implicit data. So we can also create a training set by exploiting the behavior of the users of our search service. For example, if you have a query and the users click on some documents for the query, you can assert that these documents were relevant for the query. Both the methods have positive and negative aspects. So explicit data are really clean, really accurate, but it's really expensive to create this kind of training set, while implicit data, with implicit data, using the interaction of the users, you can create a lot of data, but they are usually extremely noisy. So once that you have your training set, you run your queries against the index, you retrieve the top 1,000 documents using the standard ranking function, and then you need to represent each document retrieved by the standard ranking function as a vector of features. What are features? A feature is an individual measurable property. So you can think a feature like a signal that tells you, can help you to understand if the document was relevant or not. So given a query and a collection, we produce the feature for the documents that match the query. So examples of feature, if the query matches the title, the length of the document, the number of views, how old is it? So you can have a lot of different features, and you can try different solutions. This is also called feature engineering. So you can have really a large number of these features. So again, an example. Given a query, you extract a feature for the document that matches the query. So in this example, we have this query in the training set that is the ticker of the apple. We run the query against the index, and one of the documents returned is a page of Wikipedia about Tim Cook. So a query could be, was Tim Cook a co-founder of Apple? And the value is 0. Another feature could be, was Tim Cook in an executive position of Apple? And the feature is true. Does the query match the document title? 0, because we don't have Apple in the title. And the popularity, for example, that could be computed based on the clicks. So given the query and the document, we produce this feature vector. If we have a different document, like, for example, the information about the ticker, our vector of feature is different. So, for example, now we have the document, the executive position feature is 0, while the popularity is lower, it's 0.6. Okay, so now that we are able to represent each document returned by our ranking function as a vector of features, we want to learn our ranking function. So the ranking function will, the learned function will try to find the best combination of features that get the best ranking function. But before talking about how to learn a function, we need to be able to evaluate when a ranking function is better than another ranking function. So before, at the beginning, we did that by just looking at the results, but this is not really an analytical approach. So we need metrics. Metrics help us to understand when a ranking function is better than another, and there are two different types of metrics. So there are offline metrics that can be computed at any time, just using the training set and a ranking function. So we don't have time to go in detail on this. So example of offline metrics are precision, recall, and F-measure are really popular. Again, an example, precision. The precision is the number of relevant documents returned by your ranking function divided by the number of documents returned. So if your ranking function returned 10 documents and only 5 are relevant, your precision is 0.5. If your ranking function returned 10 documents and all the documents were relevant, your precision is 1. Another important measure that is more accurate for the ranking is the NDCG, that is the normalized discount cumulative gain, and it also takes into account the position of the document. So if your relevant documents are on the top of the results, it's better if they are on the bottom of the results list, okay? And the other type of metrics are the online metrics. These metrics are computed while the user are really using your service. So you send your ranking function in production, and then you see how it behaves with the user. So you look how the user clicked on the results, the time that took to click on something, and so on. There is a lot of literature, in academic literature about that. So once that you are able to measure how your ranking function performs over your training set, you can learn an algorithm. Again, we cannot go in detail here on how this works, but the idea is that given the query, the training set, so the list of relevant and not relevant results, and a metric, there are many machine learning algorithms that learn how to combine the values of the features in order to optimize the value of a metric over the training set. Example of algorithms that are usually used for doing that is our rank SVM or lambda mar that are usually used inside the learning to rank. Now I'm going to give the microphone to Michael that will talk about how we plug all these pipelines inside Solr.
All right, thank you, Diego. So, like Diego mentioned, and as you guys have seen, this is the standard search pipeline where you have your index that has all the documents in there. And a user query comes in, hits the index, finds the relevant documents, scores them, sorts them, and returns the top, let's say, 10 back to the client for display. And this section is what Solr pretty much gives you right out of the box. And in a standard learning to rank system, offline outside of that, you're going to have your training data, you're going to input that into a learning algorithm, and the output of that is going to be a trained machine learned model. And then what you're going to do online is you're going to use that re-ranking model, and you're going to fetch the top K best matching documents out of Solr, feed that into the ranking model, rescore them, resort them, and return the top 10 back. So what we've done with the plugin is we've actually incorporated this pipeline directly into Solr for a number of reasons, which I'll dive into. So just to kind of step back a little bit, from Solr's perspective, it provides a lot of good things for relevancy. It's very, very quick for scoring these documents, and the algorithm underneath is not too complicated. It's a bit simple, so it's certainly very easy to understand why your documents are being scored the way they are. It also provides a lot of other things like phrase matching, or you can use function queries to boost the documents based off the popularity, or maybe based off time. So maybe if your document was published this week versus a year ago, you'd want that to be incorporated in the score. You can also do things like incorporate distance, geo-distance. So if your documents are restaurants, you'd want to take into account the fact that a restaurant is closer to you than some other restaurants, so you want to also include that in your score. You can also do a lot of things on the fields. You can tokenize them, you can stem them, synonymize them, and then you can have different fields for all of those and add different boosting parameters to each of those matches. So it provides a lot of flexibility. With that, though, there are a couple issues. So you have a lot of different ways to tune the score. So one of the problems is it's very difficult to get a very perfect ranking score. So let's assume you actually spent a lot of time manually tuning this, and you got the perfect ranking query. Just because you got the perfect query now doesn't mean 6 months from now that same query will be any good. Let's say initially you tuned it on a collection that had 10,000 documents. A year from now, maybe you have 10 million. Because Solr's score takes into account the documents, the number of terms, the results will fluctuate significantly. So with that, the weights that you assign to them are actually very, very brittle. So diving into the Learning to Rank plugin, what do we actually want to get out of this? We wanted relevancy tuning to be a little bit easier, and from that you get some automatic relevancy tuning by using machine learning. And if you train your model periodically, once a day, once a week, you get that. In addition to that, since these machine learning models are actually designed to optimize all these parameters in the best way, the relevancy of your documents are also improved significantly. The other thing is we wanted a way to actually have scores comparable across collections. So take, for instance, let's say you had one collection that only had companies data, and another collection that had only people, and another collection that, say, had FAQs, right? Solr doesn't provide a way out of the box where you send a query to these different collections, and the scores coming back are comparable, so you can combine them all into a single unified list. If you train a single machine learning model from training data from all these collections and combine them and then use that same model in all these collections, it essentially treats it as if it was one big collection, so it makes the scores more comparable. Of course, we also wanted to maintain low latency. By incorporating this plugin, the learning to rank portion, directly into Solr, we no longer have to transport a lot of data outside to another service to do all this computation. It happens inside of Solr. And then we also get to leverage a lot of Solr search functionality that's already built in, so we don't have to re-implement matches on the title or anything else we want to use for features, since Solr provides a lot of that for us already. And lastly, we wanted the feature engineering process to be much simpler. Now with the plugin, these features that you write, they're all config-based, as opposed to before where you have to write a lot of code to extract the feature values for certain documents. So I'll dive into some of these coming up. So we've seen this standard search pipeline, and the Solr query, or the Solr request that you send in. Typically, let's say an example, your index had 10 million documents. It'll go through a process which will filter things down, so you have 10,000 documents that matched your query. It'll score them using TF-IDF or whatever similarity class you're using, sort them, and then you get back, say, the top 10 back out. With our learning to rank query that we've incorporated, it wraps this whole thing that we have inside the Solr query and then incorporates the ranking model inside. So now we're going to be diving into, let's say, the top 100 or top 1,000 documents, scoring those, and then returning the top 10. So how do you actually use this? So the LTR query, you'd add this one line into your config. In this case, I've named it LTR, and it's referencing our LTR QParser plugin. And so this LTR query, what it is it's actually a Solr rank query. And for those of you that don't know, the Solr rank query essentially wraps your regular Solr query and then gives you access to the documents that matched based off the regular Solr score. And it essentially gives you the top docs collector, which then you can use to do whatever you want to those documents. In our case, we're using a model to rescore and reorder those results. Solr has its own re-rank query, where instead of a model, you'd pass in a second Solr query. But again, in our case, we're passing in a model. So what does that actually look like? So inside of your request, Solr request, you add one extra parameter, RQ equals, and we have a couple parameters in here. So the first one, exclamation LTR. This is just the standard Solr syntax to reference a specific query parser. In our case, LTR references the name that we've given it in our config file. Model, that's the name of the model that you deployed into Solr, so you can reference that and use that to rescore your documents. Re-rank docs, how many documents do you actually want to re-rank? The top 10, top 100, top 1,000. And then EFI, this is the external feature information parameter. And this one's actually pretty cool. So it's actually a list of custom parameters that you would provide. There's nothing named specific for them. And the reason you'd want to use this is, for instance, let's say you have a third-party query intent system. You'd want to use that inside for your features to help you re-rank. So let's say your query was employees at Bloomberg. Maybe this third-party system identifies with 90% confidence that you want to get people documents back. So you want to actually use that information to help you re-rank your results. And Solr doesn't have a way to do that, so this is a way for you to pass in external information that Solr doesn't provide for you to help you use as features. Another one, you can use it for personalization. So maybe you want to take into account, maybe the location of, maybe North America or Europe, wherever the person, the user query is coming from, in addition to maybe a couple other things too. So you can pass all that stuff in there and then use them with your features. So we have this. The key point here, though, is that you're not actually sending the documents to the re-ranking model. You're actually extracting the features of the matching documents and sending those feature vectors to the model to re-rank. So we saw this. For this example, we had Tim Cook as a document, and we had these 4 features. Was he a co-founder, exec position, yada, yada. So really, this document actually looks in Solr like this, has a name, primary position, a whole bunch of other fields and values. So we'll actually dive into, what does a feature actually look like? In this case, we'll look at the feature, was the document, did he have an executive position? So before, in our external system, this feature is person and exec look like this. It's 10, 11 lines, a couple of statements, a for loop. It's not too bad, but it's not pretty to look at. And once you look at a couple hundred of these, it's, your head starts to spin. So now, afterwards, now that we've made it config-based, this is actually what our feature looks like, the same one. And really, the guts of it are just these 2 lines. In this example, we're looking at the category field of the current document to see if it matched person, and the primary position, and to see if it matched CEO, CTO, CFO, or president. And if the document matched those filtering criteria, this returns 1. If it didn't, it returns 0. And the cool thing about this is that actually the type that we've made Solr feature, this wraps anything that you can express inside of a regular Solr query and use that as a feature. So in my case, I'm using this exclamation terms. That's a terms query, and I'm using that as a filter criteria. If you wanted to use function queries as a feature, you can do that too. So let's say in this next one, you wanted to use a function query that takes into account the publishing date of a document. This is the equation that's given on the date boosting documentation on Solr. So this says if the document was published now, you get a value of 1. If it was published a year ago, you get a value of 0.5. And it just decreases over time. So you can use that also as a feature. So all of these features that you write, they are managed inside of a feature store. And this feature store is actually a Solr managed resource. And for those of you that don't know, Solr managed resource is essentially a REST API endpoint for you to actually send commands to do updates on Solr objects. In our case, these are feature objects. And all of these are in cloud environment are maintained on Zookeeper. And you can see here if you wanted to deploy, you'd reference your collection, the fstore endpoint, and you'd pass it your features file. If you wanted to view the features, you'd use that command. So with this, this is actually simplified our feature engineering process. Now that it's all config-based, it's a bit easier to write these. And we actually get to leverage a lot of the functionality that Solr already provides. You saw some filtering, you saw some function queries, but you can also use phrase matching, synonymization, stemming, based off whatever fields that you have. You can do that. Let's say for whatever reason you had a very specialized case for one of the features. We have support where you can actually inherit from our feature class, write your own feature class that does its very specialized thing, and then reference it in the config file through the type parameter that says, all right, this is my super specialized feature class. Use that. So this is the online search pipeline. This is what happens at query time. Offline, when you're training your model, the pipeline is very similar, where instead of a user query coming in, you have training queries, and then you're going to use the training documents, and you have to extract the features on the training documents, pass them to your learning algorithm, which will then output a model for you to use. So for that process, again, we've seen this picture. We have these 4 features for this, scoring against this document. Keep in mind the colors here. Was the result a co-founder, exact position? Did the query match the document title? So how do you actually extract these features offline when you're training? So what you do, you'd add this 1 extra line into your config. In this case, I've named it FV, and this is using a feature transformer. And what a Solr transformer factory is it allows you to add custom fields to any documents you retrieve. And in our case, the custom field that comes back with any of the documents you ask for is a feature vector field. And you notice I've color-coded the value of this feature vector field. If this FV field is the feature vector for this current document, which is the name of all the features and the values that were generated for this document. And the way you request this through just, you change your FL parameter. This is the Solr parameter that's where you pass in, say, which fields you want to return. By default, it's star, which says give me everything. But if you wanted score, star, comma, score. In our case, it's bracket FV. And the brackets, that's just standard Solr syntax to when you want to use a transformer. So now that you've extracted these features, you've trained your model, the output of that model would look like a file like this, where our model file has a name, type, features, and params. Now, the stuff that's inside params, that's completely based off the type of the algorithm. In this case, this is a lambda mart model, which is based off trees, so the params will be a bunch of trees. If you're using a rank SVM algorithm, the params would look totally different. But this is the file that you would deploy to Solr, so then we can use it online at query time to rescore the results. Our models, they are stored inside of a model store, which is also a Solr managed resource. So you would deploy and view these in much the same way that you would deploy and view the features. So that makes it a bit simple. And if you wanted to use a different scoring algorithm, right now we've done rank SVM and lambda mart. To add a new scoring algorithm, you'd inherit from our model class, and you just implement the score and the explain function, and you're good to go. So how does this all work? In our case, after re-ranking, we've actually increased our NDCG by about 10%. And for those of you that don't know, increasing NDCG gets exponentially harder. So this is a significant gain. So we're really proud of that. And then online, also, our clicks at position 1 also increased by about 10%. So that really validated the fact that with re-ranking, we did a lot better than before with regular Solr relevancy. Just to give you guys an example, for the query unemployment with Solr ranking, after a lot of tuning, we got flooded with a bunch of definitions. With machine learned ranking, re-ranking, the first result is actually the unemployment index, followed by the definition, and then you can see an FAQ, how to actually find unemployment. The other one underneath is the function or application that you can dive into that will give you a whole lot of other information on the Bloomberg terminal about this. So it's much better. Now, of course, this is just a single example, but we have a lot of examples where it was significantly better than before. And of course, performance. So we had a previous external re-ranking system, and compared to that versus our new integrated re-ranking directly in Solr, our performance improved by about 30%. Which is really good. We're really happy about that. And this was based off of a test that we did on a collection of 10 million documents, over 100,000 different queries. And we were re-ranking the top 1,000 results using 1,000 features. So just to really hit it home, some of the benefits that we got out of this is the feature engineering process is much simpler. And now that it's config-based, you don't even have to compile these unless you're going to do some specialized feature classes. We get access to the rich Solr search functionality inside, so you can leverage that as features. And of course, the relevancy over regular Solr tuning is much better when using learning to rank. And of course, if you're training your model periodically, you get built-in automatic relevancy tuning. And again, if you train a single model across multiple collections and use that same model for all those collections, the scores are actually comparable. So if you have a federated search, you can actually combine all the documents across collections into a single unified list. And lastly, you also get performance benefits because now this is actually sitting inside of Solr, and you're not sending out stuff, transporting over the wire to whatever other services you might have. So where are we going from here? We've certainly derived a lot of benefit from this plugin that we've written, so we're going to continue to work to open source this, so hopefully all of you guys could benefit as well. Also, we want to actually support pipelining multiple re-ranking models. So right now, this is actually this is the second step after the initial scoring. There's no reason why you can't have a second step and a third step and a fourth step. So take, for instance, in the second step, you want to re-rank the top 10,000 documents using whatever regular features. Let's say you also wanted to incorporate image quality to help you re-rank your results. Well, image quality is an expensive process, so maybe you only use that in a third re-ranking step, which only re-ranks the top 100 documents, and the previous step re-ranked the top 10,000 with faster features. In the same line of thinking, there's no reason why it has to be the second step. Why not also give you the capability to make it the first step, assuming that your model is fast enough to do that. So with that, that brings us to an end. If you guys have any questions, let us know. And also, if you don't get your questions answered, you can come to me, Diego, or Josh afterwards or at the booth, and we'll be there answering questions for that. No, thank you. Yes.
The number of features, how do you go about identifying what would be good features for your model? And are there X number of features that you would consider before you think the model will work?
Good question. So, Josh, you want to take that? Well, I can briefly cover that. So, knowing how many features to use, I mean, that's where the domain knowledge comes in. So, if you're supposed to be the expert on the data that you're searching, right? So, hopefully, you know what's important and what's not. If there's a limit on the number of features, well, if you're using metrics to analyze how good your re-ranking is, you'll see eventually as it keeps your metrics keep going up and up and up, eventually they're going to start to slow down. But then it's a trade-off of, well, how much more do you want to invest in that? Or do you think you've reached a good point? Maybe you should focus your efforts on other things. But yeah. Yeah.
Also, there is feature analysis. It's something that is broadly studied. And there are many studies that explain how to study the relevance of a feature in a ranking model. So, for example, if you use random forest, you can see from in the trees, your ranking model, the importance of the feature.
So for different query intents, do you have to use multiple re-ranking models?
No, you could use, you can have the same model, but a different query intent, you just have it as a different feature. So maybe you have one system that identifies if this is a person search, company search, an FAQ type search. Maybe you have a different query intent.
Actually, with the plugin, you'll also be able to load a different model based on the user. So also,
yeah, there's certainly that flexibility too. If you had a specialized trained model, you can use one or another if you wanted to make a decision based off that. In the back?
Yeah, I was just wondering how you predominantly do online evaluation, or do you offline evaluation? Do you do primarily click tracking, or do you do primarily
Right. We do both heavily. The offline metrics we use that pretty much as like a first pass, where after you've made your features, you train your model, you use the offline metrics to evaluate whether or not you actually did better or at least didn't do worse than before. If that looks good, then you're going to be like, all right, sweet, let me release this to production and see how clients actually behave. Because really, that's the telling sign if users are actually reacting to this. It could be the case that maybe your offline metrics say it's about the same, but then no one's clicking anything. Maybe that's a bad indication. Yep.
Have you looked at using the Solr scoring functionality itself prior to your re-ranking?
Yes. Yeah, exactly. So that's a good question.
Yeah, that's a really good point. So we are thinking about that. The point is that the first step that you do when you retrieve the top 1,000 documents, the target of this step is to have maximum recall. So you want to push all the relevant results in the top 10. So you could use machine learning for try to change the Solr ranking function.
Right.
This is in the plans.
Yeah, and definitely now by having this layer on top, instead of the initial problem is like I need to get that relevant result in the first position. Now it's a bit more lax. You only need to get it in the top 1,000, which is a piece of cake, really, if you spend just a little bit of time tuning. But certainly, if you could tune the Solr parameters for boosting, that'd be even better. Yeah. No, thanks.
Thank you.
Question?
Yeah, is it possible to train the model to avoid duplicate documents?
Training the model to avoid duplicate documents?
Yes, but when you retrieve 10 documents, they're not more or less duplicates of each other. For example, you want to give an example like this?
No, I understand. You can certainly build features that will detect if a document is already in the list, but Josh?
I think that in Solr, you have features for doing the duplication that you can run before, like filter. There is a filter plugin that you can use for doing that.
Something else we've looked at doing as well is after you get your construction, as kind of a third pass, we've looked at using knowledge graphs to sort of connect semantically similar results and push them together. That's not something we have built yet. That's something we might be building in the future.
Yep. Yes?
So, as you said, in future, you're going to apply the standardization step.
Mm-hmm.
So the applying step is like it increases your latencies at 29%.
Yep.
Is this feature applicable on every single Solr node, or is it only on the aggregator, which is
So this part, well, actually what happens with the re-rank query, it gives you the top docs collector at that point, which might hold the top 100 or 1,000 relevant documents. At that point, where we want to start pipelining multiple re-ranking models, we didn't dive in yet to see how you want to break that apart. Of course, right now, too, with the re-rank query, it only allows you to have a second step. Potentially, you might change that up and maybe make it a separate component that allows us to send that across to whatever we want in however many steps. But right now, it's not as flexible for that.
There was a question.
Yes. Any other? Yeah?
You've open sourced other contributions.
Yes.
This seems fairly major. Do you think you'll be able to get this open source?
Good question. So I can't put any timelines around it, but there's certainly a lot of push from the developer side of things, and there's a lot of push from upper management too. So it's looking good. Yeah. It looks like we ran out of time. But if you guys have any questions, come up to us afterwards. We'll be right outside the door too.